Now, the last little detail that we need to take care of in this concept of orbital motion is the idea of weightlessness. Now, it's not true that the astronauts are weightless. They actually do feel the force of gravity. The reason why it seems like they're weightless, or why there's no gravitational force, is because they're constantly in free fall. Just like the cannonball fired around the Earth, the cannonball just constantly falls around the Earth. And as a result of falling around the Earth, constantly falling around the Earth, they're constantly in free fall. Just like you feel weightless if you're in an elevator when it drops, or if you're in an amusement park ride and it drops straight down, you feel weightless temporarily while you're in free fall. And the only difference with the astronauts is that they're permanently in free fall until they come back down to the Earth. So let's look at the forces that are acting on an astronaut who's traveling through space. So if the astronaut is traveling in a circular motion, I know that there would be two forces that are acting on the astronauts. The free body diagram would look like this. There would be the weight of the astronaut, and there would be the normal force. So how does that look? Well, notice that these are all radial motions. One points directly in towards the center of the Earth, and the other one points directly out away from the Earth, as all normal forces on the Earth do. So, since I know that the circular motion that this guy follows as a result of these two forces, I know that mv squared over r is equal to the gravitational force, which points down. This guy is actually causing the centripetal force, and the normal force is pointing up. Now I've reversed my coordinate systems. I'm calling this direction positive and this direction negative because the centripetal acceleration is pointing down. Otherwise we'd have a negative number on the left side. So I'm picking down as being the positive direction in this particular situation. Now, the issue is that, of course, the normal force in this situation is being allowed to go to 0. So if I allow the normal force to go to 0, what that would allow me to do is to calculate the velocity that I need to travel at in order to produce this acceleration. And so just as I found previously with the previous problem, this normal force becomes 0. As long as I maintain the right speed at the right distance, then I can produce an acceleration, a downward acceleration exactly equal to gravity, and then I will no longer feel the normal force. The normal force will not be necessary. Now what happens if I slow down? Well, if I slow down, then of course the normal force, it will be actually greater than the centripetal acceleration in the downward direction, and I'll find that there will be some normal force. What would happen, for example, if I went too fast following this curve? I would begin to drift upward towards the ceiling, and I would feel a normal force from the ceiling pushing down on me because I was traveling too fast. So the key with the astronauts is that they are not actually weightless. They actually feel almost the exact same force of gravity. In fact, from the previous example, typically most astronauts only get about 300 kilometers above the surface of the Earth. So let's calculate what is the value of gravity at 300 kilometers above the surface of the Earth. Well, the value of g would be, if you remember from the previous section, we had a formula for finding that was gm1 over r squared. So in this case, we would have a radius for the Earth of 6.38 times 10 to the 6th plus 300 kilometers would be 300,000 meters, and that would give me a radius of the Earth of 6.68 times 10 to the 6th, and we know the mass of the Earth is 5.98 times 10 to the 24th. So this means G would be equal to 6.667 times 10 to the 11 times 5.98 times 10 to the 24th divided by, I wrote that formula wrong, over r squared, And then that would be divided by the radius of the distance between the center of the Earth and the orbiting spacecraft. So that's 6.68 times 10 to the 6th. And that number, don't forget, is squared. So we get 6.667 times 10 to the 11 times 5.98 times 10 to the 24 equals, divided by 6.68 times 10 to the 6th squared, and I get a value for G of 8.93 meters per second. 8.93 meters per second, but at the surface of the Earth it's 9.8. That's not an enormous difference. It's actually only a very small difference. So if we take the 8.93 divided by 9.8, we find that the value of gravity is approximately 91% of its strength. So gravity has not gone away. It's not that they're so far from the Earth that they don't feel the gravity of the Earth anymore. It's because they're in free fall. Because they're constantly in free fall, they feel like they don't have any weight because they don't feel the normal force pushing against them. But it's not really that the gravitational force has gone away. In fact, it's only just very slightly weaker than it is here at the surface of the Earth.